So, I mean, the reference for Chapter 1 is, of course, these lecture notes I told you about last week. The reference for Chapter 2 is Berger and Ford. The other chapters, I can give you references if you'd like. Okay. Any questions? Yes?
The question about your talk yesterday. So, like, all these things you talked about are like really important to be able to see anything you're interested in at the LHC, right?
Yeah.
The reason of the development is that if I'd given you a working LHC 10 years ago, like, wouldn't you be able to see anything?
Yeah. Well, sorry, what do you mean all these things
Like,
are really
so
important?
You need to really know the background really accurately, right?
Oh, in my talk yesterday.
Right.
Yes.
So if, like, all the technology that you talked about yesterday is really important so you can actually see what you want to see, and I was just wondering how recent of a development that is.
Well, maybe today when I talk about the top quark discovery, you'll get a feeling for that. So the top quark discovery actually was made 15 years ago. And it was made in an earlier stage of this technology. And they did actually discover the top quark. So the problem of finding new physics at the LHC is kind of a comparable problem. And this, the top quark cross-section, we'll talk about this in the lecture. The top quark cross-section, when it was originally discovered at 1800 GeV, is 6 picobards. And so that's kind of the cross-section level we're talking about at the LHC for discovering new physics. And the pp bar cross-section is 50 millimeters. It's kind of the same problem. And they were actually able to discover the top quark, and I'll show you how. And so if you can't compute the cross-sections from pure theory so precisely, what you have to do is to do the thing I was talking about in the question period, namely make a lot of experimental measurements and try and use your knowledge of QCD to relate those measurements to contributions to the background and then extrapolate out to the region where the new physics is supposed to be. And if the signal is sufficiently large, you can prove it's there. If the signal is a marginal signal, then it might be harder. And the higher you go in energy, the more striking a signal of new particles will be because the cross-sections go up rapidly with energy. So at every moment, there's something that you have the ability to discover. And so, we don't know. I mean, maybe the gluino mass is 600 GeV, and it would have been really easy to discover at the SSC. Maybe the gluino mass is 3 TeV, and it's going to be just a real challenge to discover at the LHC with all these precision calculations. And you always have to be lucky, right? Other questions? Yes?
The question is also about your talk yesterday. You talked about separating the amplitude into two, and of course, there's a offshore particle in between the two amplitudes.
Yes.
Then you talk about the fact that this particle is offshore is sort of contradictory to the unitarity.
Yes.
I didn't quite get this. So could you please talk?
This is some point, probably I didn't explain it so clearly, but this point is actually discussed in a very precise way in those lecture notes of mine that I put on the archive last week. So if you look, I think, in Chapter 5 of those notes, maybe Chapter 6, this whole construction is laid out in detail. But very roughly, the point is the following. Let's say you have some multi-gluon process like this. And so schematically, that corresponds to a multi-gluon amplitude. This is one diagram that contributes to that. There are many others that you want to compute. So one way to try to systematically compute these diagrams is let's break it in half. So we might, for example, by some method that involves unitarity, split this into two parts. Okay. And then if we can compute each half separately, then maybe we can glue them together and find the whole amplitude. And if you have this MHV formula that I discussed, then there's a big advantage in that, because this guy here, oh, let's add it. Okay. This guy here is a 1, 2, 3, 4, 5, 6, 7-point diagram. And maybe I'm interested in one for which the MHV formula doesn't apply, like 3 minus signs and 4 plus signs. But for a 5-point diagram, all the amplitudes are either MHV or the complex conjugate of MHV. And so I can just write down the answer. It's very simple. And similarly, for a 4-point diagram, I can just write down the answer. So in principle, I could have a construction like this, where you write down the answer for that, you write down the answer for this, you sum over some things, and you get the answer for this much more complicated diagram. Now, the reason that's subtle is because you know that whenever you have an intermediate line of a Feynman diagram, it's off-shell. And whereas the results for these MHV amplitudes are extremely simple when everything is on-shell, as soon as you go off-shell, things become gauge invariant, all kinds of complications occur. The formulae are not simple. And so typically to go from here to here is a total mess, because this expression has all these non-gauge invariant factors, and when you add them all up, they cancel. And in any individual diagram, they might be the largest contribution. So what I described yesterday is a very beautiful result due to Freddie Cacciazzo and his colleagues, where instead of doing a sum over off-shell momenta, you do a sum over on-shell, but complex-valued and unphysical momenta. Okay, but the momenta are on-shell. That is, you have a momentum here, Q of z, and Q of z has complex components. So it's actually an unphysical momentum, but Q of z squared is 0, so the momentum is on-shell. And then using that technique, you can do exactly what I said. You write down MHV amplitudes. They're extremely simple. You multiply them together. You add them up in a certain way. You get the result for 7-point, 8-point, 10-point gluon diagrams. It's a total magic. And if you look at my lecture notes, you'll see how it works. Yes?
Sorry, why are we using on-shell gluons if gluons always intermediate particles?
Oh, yeah. But in all the calculations I've been doing, I was taking as an approximation that the final particles are on shell. Now, in reality, they're off shell by an amount of order 1 GeV, and they're embedded in processes with momentum transfers of 100 GeV. So that's actually a pretty good approximation. And if you take them off shell, I'm not sure what you really do with them. I mean, you have to put them in QCD bound states. And we don't know how to analytically treat the QCD bound states that involve quarks and gluons. There's just a phenomenological picture. Whereas if things are on shell, then you get very precise and simple answers. And so the idea is to first get those answers, and then you modify the answers slightly using some phenomenological model of how the gluons turn into hadrons. So that's a much cleaner way to do it than doing all these calculations with the gluons off shell. Okay? Other questions? Okay, so yesterday we talked about the flavor structure of the standard model, and I think we really made a lot of progress yesterday. Not only did I tell you where the masses come from in the standard model, which is something that I actually owed you from some, maybe even weeks ago, but we found out that certain properties of the standard model, the fact that the individual 3 lepton numbers are conserved, the fact that there are no flavor-changing neutral currents, like S to D and Z boson emission, even the phenomenology of parity and CP violation that we see in nature in elementary particle physics reactions in any event comes from the Standard Model. So let me write those points again. The conservation of the electron, muon, and tau number as separate quantities. The absence of flavor-changing neutral currents. For example, S to D plus C0. The fact that the strong and electromagnetic interactions conserve C, P, and T. The weak interactions conserve CP and T up to the effects of the heavy quarks, bottom and top. And these guys lead to CP and T violation. All of these are qualitative features of elementary particle physics as we observe it. And they all come out just simply from the structure of the Standard Model. So you can write down the most general Lagrangian, which is gauge invariant under SU3 cross SU2 cross U1, do appropriate changes of variables of the fields, and the thing you get satisfies all of those properties. I should say again, there's one footnote here, which has to do with the axial vector anomaly. And that's something that you actually have to patch up. But once you fix that, this is actually a correct statement. OK, so now we're really in the end game. Now what we have to do is just discuss the last couple particles of the Standard Model, which are the heaviest and have some special properties. And those are, we discussed already the W and Z. So what's left is the top quark and the Higgs boson. And so today the top quark, tomorrow the Higgs boson. So the top quark lives in an SU2 doublet with the bottom quark. I already told you on Tuesday that we know basically everything about the quantum numbers of the bottom quark. We know, for example, that when the Z0 decays to bottom quarks, there's some radiative corrections which involve the top quark and the W, which shift this decay rate by 2%, and that shift is observed. And so we not only know that the bottom quark is in an isodoublet, and it has isospin -0.5 and hypercharge, well, 1/6 here. We know that the right-handed bottom quark is a singlet. Not only do we know all those things, but we really know very precisely that the values of the couplings are exactly the same as for the other quarks in the Standard Model. So that should immediately tell us that we should really understand the top quark. As long as the theory is weakly coupled and there are no interactions beyond the Standard Model, there's basically no freedom in the properties of the top quark. We should just be able to work them all out and compare to experiment, and it should just work. And so let's use the Standard Model and discuss that and see how we do. OK, the top quark is unusual among quarks because the mass of the top quark is about 170 GeV. So this is not a this is a large mass, but I think people differ on whether this mass is an enormous mass that requires a special explanation, or it's an ordinary mass. So the top quark has an ordinary mass scale, and the other quarks are very light. And I incline toward the latter view. The Yukawa coupling for the top quark is just about 1, which is to say lambda t squared over 4 pi is about 1 over 13. And you remember the value of QCD, alpha s over 4 pi, is something like 1/9, 1/8, or 1/9. Alpha weak over 4 pi is something like 1 over 30. So I think it's fair to say this is of the same ballpark as those estimates. It's not the strongest coupling in the standard model. Probably, I think one might try and build a theory of the Yukawa couplings by saying this number is of order 1, and all the other Yukawa couplings are somehow maybe obtained from that number by doing perturbation theory. That's certainly an approach that a lot of people have tried to explain the spectrum of the quark and lepton masses. So I'm going to treat the top quark like an ordinary quark with exactly the couplings that it's supposed to have in the standard model, and I'll treat those couplings in weak coupling perturbation theory. But the top quark has one feature which is very different from all of the other quarks, which is that the mass of the top is greater than the mass of the W plus the mass of the B. So instead of decaying through the weak interaction effective Lagrangian that we wrote down last Friday, a top quark can just decay to the W boson. So whereas a bottom quark would decay to, let's say, a charm quark, there would be this Fermi interaction, G squared over MW squared, and then out of this would come some quarks or leptons. For the top quark, it's completely different. The top quark turns into a B, it emits a real W, and then sometime later, let's just say a long time later in elementary particle terms, 10 to the minus 23 seconds or something like that, the W decays into whatever its decay products are. And remember, we already worked out the decay products of the W, so this is going to go to 11% to E nu, 11% to mu nu, 11% to tau nu, 34% to UD bar, and 34% to CS bar. And when I made that discussion, I left out the Kabiba mixing. There's a couple percent of US and CD. Okay. And so there are two consequences of that. One is that you remember this formula has a 1 over 192 pi cubed in the denominator. And that comes, as you guys know by now, from 3-body phase space. Here there's only 2-body phase space, so there's no small factor like that. And in general, this decay is completely open. So what we expect is a formula that's more like alpha weak times the mass of the top divided by 4 pi or 8 pi, something like that. So this is GeV in mass scale. And I'll work out that formula precisely in the course of the lecture. Okay, what does the top quark look like? Well, that picture gives it to us. There are basically two main modes of top quark decay. We always get a BW, and then the W can decay either to a lepton or to QQ bar. If it's QQ bar, this system has the mass of the W, so it's an 80 GeV dijet system, and in this case there's a lepton at missing energy. So now it's kind of obvious what top quark events look like. You look for events with something like this on one side and another pattern like this on the other side, and I'll show you some events in a moment. How do you produce top quarks? You can produce them in quark-antiquark annihilation. Quark-antiquark annihilating to a gluon, which would then produce a pair of top quarks. You could also annihilate gluons, and so the gluons can produce top quarks by actually any of these three diagrams. And you need all three of them for gauge invariance, as you guys know. Now, this cross-section is intrinsically a lot larger than this cross-section. This is basically alpha S over alpha times the E plus E minus annihilation cross-section. This, in principle, is a lot larger because it's not an S-channel process, it's a T or a U-channel process. The difference between these cross-sections is seen rather strikingly in the dependence on energy. At the tevatron, at 1800 GeV, so this is a PP bar collider, at 1800 GeV, practically the only partons in the proton that have enough energy to make the top quark are the valence quarks and antiquarks in the proton. Here it's 6 picobars. If I go up just a little in energy, then I get more valence quarks and antiquarks able to participate. The cross-section actually goes up markedly to 7 picobars. At the LHC, at even 7 TeV in the center of mass, you're now at high enough energies that the gluons from the gluon C can contribute, and this process turns on. And so at this energy, you expect something like 150 picobars. And actually, in the first year of the LHC, the cross-section's been measured. That's actually the right number. So a dramatic increase in the size of the top quark production cross-section for, you see, it's only a factor of 3 or 4 step in energy. But the reason is that with that step, you can dig into that big sea of gluons, you remember, that exist in the proton at relatively small values of the energy fraction. And then this process here turns on. When you think about top quark production at the LHC, this is actually really interesting. A quark, and the LHC is a proton-proton collider. So you'd think that if you make a quark, it would be really different from making an antiquark. But if you're making everything in gluon-gluon collisions, actually at the parton level, it's a CP invariant final initial state. And so then you can imagine doing CP tests and things like that in top quark decays. And that may actually be interesting to do. OK. Now I guess I should talk to you first about what top quark events look like. And I have some pictures of them in the transparencies. On page 2, there's a very interesting event discovered actually way back in 1992 by the CDF experiment. It's very striking. There's several views of that event which are on this slide. Over on the left is the tracking view looking down the end of the detector. And you can see they're labeled 4 very clear jets and an electron viewed in the electromagnetic calorimeter. Up in the upper right-hand corner is the Lego plot. And it shows the same information. An electron, 4 jets, and they fit. They don't know where it is in cosine theta or rapidity, but the transverse momentum of that neutrino is known. And so if you believe that the neutrino is actually together with the lepton and coming from a W, you can make a complete kinematic reconstruction of the event. If you take the tracking picture and you blow it up, then you get the picture which is just to the right of that, and you see that there are suggestions of vertices. And actually, if you blow it up more, you can see that there are 2 vertices that are actually resolved. So, in fact, what the event seems to be is TT bar goes to BW, BW, where one of these W's is going to a 2-jet system. The B is going to a tag jet. The other B also goes to a tag jet. And the W goes to an electron and the neutrino. On page 3, I have another picture of a top quark event. And maybe in that case, the blowing up is a little clearer. This is a different event from, I think, run 2 of the tevatron. And you can see that, there are 2 B vertices identified, multiple jets, a muon, and missing energy. So this is the characteristic of these events. And I think on the next page, this would be page 4, there's an event from D0, which is supposed to be a 6-jet top quark event. That is to say, an event where both W's went hadronically. In this picture, there's not a vertex, but there's another feature which is interesting. There's a jet, and then there's a muon, which is at relatively small transverse momentum, but definitely outside the jet and associated with it. And this kind of thing happens when you have a B decay to a muon plus, or maybe I should say a bottom meson, but it's really a B decay to a muon plus muon neutrino QQ bond. So there's I think there's at least one of those jets. Those of you who are looking at this in color, it's probably if you look at the second jet from the left, the big tower, you see a little thingy next to it. That's a muon, which with some probability will tag that jet as a bottom. Okay, well, now at this point, maybe it's interesting to discuss Maita's question, because there is actually an issue here. The top quark discoveries began to be announced when the Tevatron began operating, and there was a lot of confusion about it. Mr. Dalitz, the inventor of the Dalitz plot that you folks struggled over in the first problem set, actually wrote a paper with some colleagues claiming that the mass of the top quark was 135 GeV based on some events that were found at CDF. And the events, what can I say, looked like this. So the problem is that events that look like that aren't necessarily from top. They can come from other sources. And in particular, a very important source of events that can confuse you come from the process PP bar going to a W plus jets. So for example, I could have a process where I have QQ bar radiating a W, which then goes to E nu. It radiates a couple gluons. One of these gluons splits to BB bar. That's certainly an allowed process in the standard model. And maybe this gluon also splits to 2 ordinary quarks. And so now I have exactly the final state that I wrote here, an electron and a neutrino, 4 jets of which 2 are B-tagged. And so now or maybe this split to CC bar, which is probably 20 times more likely. And then the charmed quark lived long enough to fake the displaced. Well, I mean, the charmed quark lives about, has, depending on which charmed quark it is, a factor of 2 to a factor of 10 shorter lifetime than the bottom quark. But nevertheless, a long-lived charmed quark can fake that signature of a long-lived decay. So it's not at all unlikely that an event like that could show up in your detector looking exactly like that first extremely beautiful event that I showed you, and maybe that's what it is. So to understand this, you need to think about this in a somewhat more sophisticated way. So the way people tried to think about that is to try to collect data on this reaction and to use that data to model the background in the top quark search. So I guess on the next slide, what I show is some data that CDF actually collected on W to E nu plus N jets. And you see the transverse momentum distribution of the first, second, third, and fourth jet in W plus jets reactions. So these complicated processes like this are observed, and their cross-sections are measured. The cross-section would be measured in that plot without any tagging. So these would be some generic quarks and gluons that come in the final state. Now you can do the following analysis. Let me try to measure the rate for PP bar going to, let's say, e nu or mu nu plus n jets, where for the moment I'm not prejudiced against n. But I insist that, for example, one of these jets is b-tagged. So one of these jets has a displaced vertex that I can determine in the way that you saw in those pictures. So now you can make a diagram like this. For 1, 2, 3, and 4 or more jets, you can make a histogram of what you observe. So this number, this number, this number, and this number. The cases of 1 and 2 jets, when you do an analysis like this, are completely dominated by W plus jets, and in fact completely dominated by events in which the final state quarks aren't B quarks, they're charm quarks, or maybe even light quarks, which by some accident faked the appearance of a displaced vertex. But you know what these cross-sections are. You've measured them. You measure the probability that a charm quark would fake a bottom quark, or a light quark would fake a bottom quark. And by working extremely hard, you can make an estimate of what the expectation is for W plus jets events that come in that channel. And similarly, in the 2-jet channel, you can use the data on W plus 2 jets and make an estimate for what should appear in that channel. Now, once you've understood how to do that, these estimates normalize the W plus jets background. And the interesting thing is that these estimates fall in a very regular pattern. And so having hopefully, and maybe I should say this takes tens of man-years of work in analyzing the data on this reaction, having understood the rates that are occurring in these two events as a combination of the fundamental cross-sections and the properties of the detector, you can then predict what rates for W processes are going to occur in the events with higher numbers of jets in the bins with higher numbers of jets. And then if you observe a significant excess in those bins, you can have very good confidence that that's not coming from your W plus jets background process. It's coming from a new particle that you could observe. And so what's important here is to understand very clearly that you're getting the correct numbers in these bins and to understand the trend in this plot, which now this is the completion of the answer to the question, Maida, that you asked at the beginning of the lecture. This is much easier than from first principles calculating what should be in that bin. And so if you go to the next slide, you see actually the current status of that in CDF. So let's see. You guys don't have it in color, but why don't you turn around and look at this in color? Okay. So the green, the various shades of green on this plot are W plus jets processes, where the different shades are the charm quark faking Bs, real Bs in W plus jets, etc. Where the green gives out, and in the 3 and 4 jet bin, there's a large discrepancy between the green and the actual normalization of the data. That discrepancy is now made up by the new process that we're looking at, TT bar. And maybe I should also say there's another check on this, which is that if I insist that there are 2 B-tagged jets, well, if I had the W decaying to charm here, the probability that a charm can fake a B is 10%, but the probability that 2 charms can fake 2 Bs is 1%. And so this sample, in which there are much fewer events, should be a much purer sample of actually bottom quarks. And if you now look at this sample, you can see that there are much larger excesses with the background normalized by some similar kind of an estimate. So what can I say? There really is a top quark, and even though there are individually on an event-by-event basis, you can't really tell which ones are the top quarks and which ones are background. There are systematic techniques that you can use to show that the background cannot account for the signal that you're observing. In the next couple slides, I just have some kind of snapshots of the distributions that come from these events. So you see in the 3 and 4 jet bins, you're getting now a pretty pure sample of top quarks. And so you can then just try and plot up the distributions from those events and see what they look like. If you, for example, look at doubly B-tagged events and you look for the 2 jets that are not B-tagged, or if you look at 4-jet events and you pick the 2 jet events that are, if you like, most likely to come from the W by some measure, and you plot them up, indeed the distribution peaks at the W mass. And so there do seem to be W's in those events. And then if you now combine a 3rd jet with a W, you get the mass distribution that's shown on the next page. And here, what you see is that the peak is very clearly in the neighborhood of 170 GeV. And now if you try and analyze those events very carefully, the likelihood is maximized for this analysis, a mass of 173.1 plus or minus 1.2 GeV. So that's frankly pretty impressive. This is a part per mil determination of the mass of a quark. Oddly, the top quark is that quark for which the mass is most accurately known. Okay. Yes?
Speculate that the top quark may be actually a bounce state or things, just speculation?
So far, yeah. So the way you would find that out, I think, is that if the top quark is a bounce state, its cross-section would not be exactly what QCD predicts, and its decay pattern would differ from what's expected in QCD. And so if you basically just write down the standard model predictions and try and test them precisely, we'll get some insight into that. And so I'm going to go more into this as the lecture proceeds. Okay. Maybe I should also say that top quarks can be found produced at the tevatron singly through various reactions. So one way is if I have UD bar annihilation, that can produce top and bottom through a W exchange. This is the so-called S-channel single top production. Another thing that you could have is the following process. If I have a gluon from the initial state can split into BB bar. And now a quark can scatter that BB bar into a top quark by the exchange of a W in this channel. So this would be somehow up to down, or I guess it would actually, well, yeah, let's say up to down from a proton coming in here, and the gluon would come out of an antiproton like that. And then the bottom would be turned into a top quark. And so this process is actually the dominant one because it's got the W in the T channel rather than the S channel. Yes?
Is that diagram of the conserved charge?
Yes. UG bar by the W by the TB bar.
Sorry, does time go up?
Time goes up. In both of these diagrams. So this is, as I said, an S channel, and this is a T channel. So this diagram is actually larger. An interesting property of this diagram is that there's a correlation between the direction of the top quark and the sign of the top quark. So a W plus goes from the proton, and in this case you get a top quark which is more, actually more in the direction of the P p bar, if I reverse the diagram, then I would get an anti-top in the direction of the p. And so that correlation you can actually look for as a way of extracting the signal. And very recently, this single top production was also observed. I think there's a slide from that observation, but I think I won't go into it in great detail. OK. So now the next thing I wanted to tell you about is the decay properties of the top quark. Let's see. Oh, yeah, they're here. So in principle now, we could go compute the decay rate of the top quark. But something that's actually very interesting is to look at the helicity structure of top decay. So I'm going to try and compute all the helicity amplitudes and then put them together and make an overall picture of top quark decay. And so I just want to think about the process at the original particle level, t goes to b plus w. The matrix element is g over the square root of 2, u bar for the b, gamma mu, always left-handed projections on the spinors, and the polarization vector of the w. So let's put the top in its rest frame with its spin along the 3-axis. So u of t is the square root of m top, 1, 0, 1, 0, like that. And the left-handed part of it is this part here. The bottom quark, let me take, moving at an angle theta b, and so u of the bottom quark, I'm going to ignore the mass of the bottom quark, will be 2 EB, and then there'll be a sine theta over 2, cosine theta over 2. I think with these conditions, there's a minus sign there. Yeah, I got that right. OK. And then you can just go ahead and compute the current that comes from that. So the current that we need is u bar b sigma mu ul of t. And when you work that out, you get the following thing. The square root of 2 EB times MT times, let's see, it's the overlap of this with this. So there's some overlap from the 1 proportional to sine theta over 2, 2 terms proportional to cosine theta over 2, a term sine theta over 2. And let me just take the signs from my notes. Minus, 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 minus I, and plus. And so now I want to take this vector and dot it with the polarization vector of the W. Yes?
Why that Microsoft weighted direction is g over square root of 2 instead of just g?
Ultimately, it's because the W plus is A1 minus IA2 over the square root. Okay? Good. Okay. So now there are basically 3 choices, one of which, so the W can be in any of 3 polarization states, positive helicity, negative helicity, or zero helicity. The positive helicity and negative helicity cases are pretty straightforward. Let me just do the case of a left-handed, so for a right-handed or a left-handed W, if the W were going along the 3-axis, then these polarization vectors would be this and this for the W parallel to the 3-axis. If I rotate the W's into the direction opposite to the V quark, then what I'll get is 1 over the square root of 2. There'll be a a cosine theta b and a sine theta b here. W's in the final state, so we can complex conjugate this. So there'll be a minus I here, and then a plus I for the case of the left-handed W. And one more thing I have to get right. There's a minus sign here. Because I'm basically turning it around into the opposite direction from the bottom. Okay, if you dot these two vectors together, the following thing will happen. If I dot this with this, I get a plus. If I dot this with this, I get a plus. If I dot this with this, I get a minus. So the top quark does not go into a right-handed W and a bottom quark. And if I dot with this vector, everything will add. And so I'll find that the top quark does go to a W left and a bottom left. And what the matrix element looks like is the matrix element should look like cosine theta over 2. Well, let's see. Here it's cosine theta over 2, cosine theta. Maybe I should write down what this is. Cosine theta over 2, cosine theta, plus sine theta over 2, sine theta. And then in the top case, it's minus cosine theta over 2. And you can see that this is exactly cosine theta over 2. In this case, they add, so you get a matrix element proportional to cosine theta over 2. Cosine theta over 2 is the square root of 1 plus cosine theta. And when I square it, I'll get a 1 plus cosine theta b angular distribution. So for this process here, top goes to W left, B left. The angular distribution is 1 plus cosine theta of the bottom quark. Now, why does that happen? Well, I think it's pretty easy to understand. The original top quark had this angular momentum. If the direction favored by this analysis is to have the bottom quark go this way and the W go this way, the spin of the bottom quark is always left-handed. The spin of the W is left-handed, and it's a whole unit in that direction. So angular momentum works out maximally well. If the W were right-handed and the bottom quark were left-handed, this vector would be flipped around. It would be a spin 3/2 state, and that's incompatible with the spin 1/2 initial state. So once again, the helicity dynamics tells you that this process doesn't go, this process does go, and it explains the angular distribution. Now, however, there's one more thing which is trickier. And that is there's a third possibility, because the W is massive, there's a third possibility, which is that epsilon of the W is that the W could have helicity 0. So in the rest frame of the W, that's the vector 0, 0, 0, 1. If I now boost the W to some energy, I get the Lorentz boost of this expression, which is the momentum of the W divided by the mass of the W, 0, 0, the energy of the W divided by the mass of the W. So please notice, this is a vector whose square is -1. This is a vector whose square is -1. This is exactly the boost of this vector when I put the W in motion. This is very weird, because As the W becomes relativistic, so the energy much larger than the mass, this becomes kW over m times that, which is basically the momentum of the W divided by the mass. So there are two things that are weird about that. One is that the polarization vector of the W, viewed as a vector in space, becomes collinear with the momentum of the W, which is not really something you think about for a polarization vector. The second is that it grows enormously with the boost, proportional to the momentum of the W. So those are two weird things, but Lorentz invariance is correct. And that's what it says. If you take that vector and you boost it, you get this vector. And so there's not much we can do about that except just follow the analysis to its conclusion and try and understand it. You had a question.
That's an epsilon vector should be 1, 2, 0, 1.
Sorry?
That's the epsilon vector, yeah, that like 0, 0, 0, 1 is not the vector of the physical particle.
No, it's a polarization vector. So if I have a spin 1 particle and I go to the rest frame, it has a polarization vector. And there are three possibilities, which are the three vectors that are space-like in that frame. So a spin 1 particle can be polarized along x, along y, or along z. This is the one polarized along z.
Does it make sense saying that you see it?
Well, so I'm in the rest frame. There are three possibilities for the polarization vector. Now, what if I'm not in the rest frame? It's the same three vectors, it's just I have to boost them to the frame that the W is in. Right? If I did this calculation when the W was at rest, I would use this for the polarization vector. If I do the calculation in another frame, then I'd have to use a different vector, and I'd obtain that vector by applying the appropriate Lorentz boost to this vector. And as I say, when you do that, you get a weird answer for this particular case. But let's just live with this and try and understand it. Okay, so now the next thing to do is to rotate this vector into the appropriate orientation. So that gives k over mw minus cosine theta e over mw 0 sine theta e over. Sorry, this is a sine. This is a cosine. Good. Okay, now let's dot this momentum into this one. And you can see you get cosine, sine, cosine, sine. Everything works out that the amplitude is proportional to sine theta over 2, or d gamma d cosine theta is proportional to 1 minus cosine theta. So for this process, it's backwards. But again, that's really easy to understand. The bottom quark is polarized that way. Here's the original top quark. The W has helicity 0 in this decay. And so the angular momentum, again, works out maximally well in that orientation. The odd thing is the normalization. The normalization gets this factor of E over n. And so instead of having, as we had over here, a factor g times the square root of EB times m top, we get another factor of E over m. Now, E is of order the top quark mass. Let me just write mt over mw. And so there's another factor of mt over mw. Actually, what we get is mt squared minus mw squared over 2mt. But basically, this amplitude is enhanced by a factor of mt over mw. So oddly, this process is the dominant one. And this process here is slightly subdominant. MT over MW isn't a large number. It's 2. But nevertheless, this decay rate will dominate the other one. So now what's going on here? What's the origin of this enhancement factor? Well, I'd just like to remind you that the top quark Yukawa coupling is equal to, the top quark Yukawa coupling, the top quark mass is equal to the top quark Yukawa coupling square root of 2v, and the W mass is the weak coupling, G over 2v. So the ratio MT over MW is actually equal to the ratio of the top quark Yukawa coupling and the weak coupling. And there's some other factor of the square root of 2 that comes in. Isn't that right? Yeah, I think I did. So if the top quark is heavy, then its Yukawa coupling is larger than G. Now, what does that have to do with anything? Well, remember I told you when we discussed the Higgs mechanism on Monday that the way the W gets, the W when it's massless starts out with 2 polarization states. When it's massive, it gets a 3rd polarization state. And the way it gets that state, I said in a very hand-waving way, was that it eats the Goldstone boson associated with the spontaneous symmetry gradient. So I think at that time, Sean asked me, well, is there any physical manifestation? So let's just pretend that what was going on here was that we literally had Goldstone boson emission. The top quark, we turn off the gauge interactions. Then the top quark could decay to a charged Higgs boson like that. And this particle here would be the Goldstone boson associated with spontaneous symmetry. The amplitude for this process, this, by the way, would have 0 angular momentum. So its production dynamics would be exactly the same as the process that I've just computed. And the magnitude would be lambda t times these things, the square root of EB times MT. So, in fact, if you do all the numbers very carefully, all the factors of 2 work out right. And the rate of this process turns out to be the leading term in MT over MW in the expression that I've derived. So this is actually the physical manifestation that you were looking for. The result turns out to be completely general. A highly boosted W boson or Z boson, any boson that gets its mass through spontaneous symmetry gradient, the production of the 0 helicity state, the one which is not there when the particle is massless, the rate for that is equal to the corresponding process for production of a Goldstone boson, a little piece of the Higgs sector, that boson 8 become massive. Okay? And as I say, there are many more examples of this. And if you look in the last chapter of my textbook, there's actually a proof of this identity, which is called the Goldstone boson equivalence theory. Okay. Well, finally, let's just put this all together. There are 2 main results that I've derived for you. One is that we've actually done all the calculations to compute the decay rate of the top quark. And so let me write the formula on the blackboard. It's got an alpha W over 16. There is, as I said, this enhancement of MT over MW. So when I square this thing, there'll be an MT squared over MW squared, and then there's a factor of MT. There's a 1 plus 2 MW squared over MT squared, and then the phase space is 1 minus MW squared over MT squared. And then actually this comes squared. One factor of that is from phase space. If you evaluate this number, it's about 2 GeV. With radiative corrections, I think it's 2.1 GeV. with the order alpha S corrections for m top in its correct value of 173 GeV. The angular distributions are 1 plus cosine theta for the right hand for the decay to a left-handed W, 1 minus cosine theta for the decay to a helicity 0 W. And the rates are the branching ratios, if you like, to a right-handed a helicity 0 or a left-handed W. This should be 0. This, when you put in the numbers, is about 70%, and this is 30%. So now the question is that right? This is really quite interesting because you see this analysis tests in some detail the physics of the Higgs mechanism. Where did the W, how did the W get mass? How did the W acquire its longitudinal component? So we can test this in the following way. Let's say that we can reconstruct an event where I have a top quark that decays to a W going, let's say, to lepton neutrino and a bottom quark. So let me now find the frame of the W. And what I'd like to do is to look at the following distribution. So the W is going in this direction. I want to pick my axis going along the W momentum. And I want to look at the direction of the lepton with respect to the W momentum in the W rest frame. That basically diagnoses the helicity of the W. So if the W is right-handed, the lepton is right-handed, it tends to go forward. It's one of these spin 1 processes. So this distribution is 1 plus cosine theta squared. This distribution is 1 minus cosine theta squared. And this distribution, it turns out, is sine squared theta. So let me get a sample of top quarks, take the W's to the rest frame, measure this angular distribution, and see what it looks like. And please notice that angular distribution is predicted up here. It should be, I think, 70% this, 30% that, and extinguished in the forward direction. And so on the last slide here, I have the measurement of that distribution from CDF. And you can see that it has exactly that property. It's dominated by the longitudinal mode. It peaks in the center. There are extra points at negative cosine theta corresponding to this mode here. And the data is, of course, limited in statistics, but it's totally consistent with going to 0 in the forward direction. And I think from this data, it puts a bound of about 5% on the possibility of the W decay to, top decay to a right-handed W. So very interesting. We now actually know that the top decays by a V minus A interaction. It's going to left-handed bottom quarks and either left-handed or longitudinally polarized W's. And the dominance of the longitudinally polarized W is actually some experimental evidence that the W acquires its mass through the Higgs mechanism. OK, there's just one more thing I wanted to say about this polarization analysis. You remember that when we studied the mu decay, we showed that the muon decay to a lepton, the d gamma d cosine theta for the lepton direction with respect to the muon spin. Let's look at mu plus to L plus. Then this L plus would be right-handed. And this distribution in that case we showed was 1 plus cosine theta. For a mu minus, everything gets flipped around. It's 1 minus cosine theta. The argument that we used for that was to take the 4 fermion vertex and do a Fierz transformation on it. And then we had a correlation between this spinor and the spinor of the lepton. In this case, it's still a 4 fermion process. We have the W propagator here. But the argument still works. And so this is also a correct prediction for the top quark decaying to a lepton. And this is a very strong distribution. It has a 0 at one end. So this is more or less the best you can expect to get for a polarization analyzer using spin-and-a-half particles. So the statement here is that the lepton direction tracks the top spin as a maximally effective polarization analyzer for a spin-and-a-half particle. And so when we do LHC physics, if we see top quarks coming from funny places, we'll actually be able to analyze their polarization by reconstructing their leptonic decays. And so that's an interesting tool that hopefully will be applied in the future. OK, that's what I wanted to tell you. Thank you very much. Tomorrow, the Higgs boson. And then we've done everything that there is to know about the Standard Model.